students, and welcome to Saurash's classes. Today we are here to solve some of the past year's questions of I.E.S. and beginning with, we are here to focus on section B, question number 3. You can easily download the question papers from the online site. Okay, so jumping to the question 3 part A. So here they have provided us with this is a game theory question. I'm not going to write the whole question because you can easily see it in the question paper. So part 1, they are asking us to define the definition or what is Nash equilibrium. Okay, so define a Nash equilibrium in pure strategies for this game. So they have defined a game where in the second part I will be coming to that portion. Okay, so what is basically Nash equilibrium? Nash equilibrium. See, there are in a game generally there can be various types of strategies and including payoffs, right? So Nash equilibrium refers to that particular payoff where both the players or all the players of the particular game are better off. And in that situation where no other player is changing their strategies, then only both the players we can say that they are doing their best by choosing that particular payoff of the game. Okay, so if I have to define it in a very formal way, then I can say that Nash equilibrium refers to the situation where both the players' strategies provide them to be at a position where they both are better off, provided that no player changes their strategies. Okay, so this can be treated as a formal definition of Nash equilibrium, and for further information we can also write that who actually invented this Nash equilibrium. It was invented by John Nash. Okay, also there is one very important thing we need to take into account, that Nash equilibrium are not always one single thing. That means there can be multiple Nash equilibrium in a single game. Okay, so this is also a point that we can include it under the definition of Nash equilibrium, that there can be multiple Nash equilibrium. So it is not always that Nash equilibrium has to be unique in a particular game. Okay, so this is about the first part of question number 3. Now moving to the next part. Okay, so in 3 part B they have provided us with a game. So this is player 2, player 1, okay, so this is S to 1, S22, S11 and S12. So this represents player 1, okay, so this is their strategies, and player 2, these are their strategies. The payoffs are given as 0 and 12, 12 and 0, and finally we have 3, 3. Okay, so what is the thing that they are asking us? Show that the unique pure strategy Nash equilibrium is not Pareto optimal. That means we have to find here the Nash equilibrium, and to answer this question we also have to know that what exactly is Pareto optimality means. Okay, otherwise answering to this question will be a bit difficult. Okay, so we already know what is Nash equilibrium. Now moving on to how to find a Nash equilibrium. Okay, so starting with the situation when player 1 chooses his strategy S1 dash. Okay, so when player 1 chooses S1 dash, then what is the best payoff that player 2 can choose, given that player 1 has chosen S1 dash? So one more important thing we have to take into account in this, that this first payoff represents the payoff of the first player, okay, and the second one, that is here it is 10 and over here it is 12. This represents the strategy for the second player. Alright, so coming back to our thing, that player 1 has chosen strategy S1 dash. He has declared it, and also they have also mentioned it that this is a simultaneous move game. Okay, so this is a simultaneous move game. So they know their strategies. That means player 1 is revealing his strategy to player 2. Now player 2 can choose based on what player 1 has already chosen. Now see, we have to think in this way, that whether 10 is more or 12. Here they have not given us with a negative sign, so these things, these payoffs are all positive. So it's very easy to decide that whether 10 is higher or 12. So it's very easy that 12 is higher. So if player 1 chooses S1 dash strategy, then player 2 would definitely choose S22. Why I am writing S22 and not 12? Because this 12 comes under this S22 strategy of player 2. Okay, so in bracket we can write that, which is 12. Okay, then coming to the situation when player 1 goes for strategy S12. So in player 1 only, when it chooses strategy S12, then which is the better payoff to choose from the perspective of player 2? Here we have to see again the second element of the payoff, that is whether 0 or 3. We have to compare between 0 and 3. And it is very much visible that 3 is higher than 0. So here again player 2 would again choose strategy S22, but here the value of the strategy is 3 over here. So writing it, then player 2 would choose again S22, but this time it is equal to 3. Alright. So player 1 portion we have done. We are done. So now we have to do or repeat the same step from the perspective of player 2 now. Okay. So erasing this part. Alright. Now player 2. If player 2 chooses strategy S2 dashed. That means what? So player 2 is choosing or playing S2 dash. Now, I have already told you, now we have to look in the first part of this payoff, which represents the payoff of player 1 only. Right? So we have to now compare between this 10 and this 12. So here again 12 is higher than 10. So player 1 also goes for the S1 2. Player 1 chooses strategy S1 2, which is having the value of 12. Okay. And similarly, if player 2 chooses S2 2 strategy, then player 1 would again have to compare between 0 and 3 over here, and that represents, he would again, that means player 1 would again go for the strategy S1 2. So player 1 chooses S1 2, but this time the value is not 12 but 3. So if you could recall that when we played the game from the perspective of player 1, player 2 was choosing only S2 2, right? Again, playing the game from the player 2's perspective, player 1 is again choosing the payoff of S1 2 in both the cases. So from this we are getting that yes, the Nash equilibrium do exist, and it exists in a payoff of where S1 2 and S2 2, where the payoff's value is nothing but 3 and 3, 3 comma 3. Okay, so this is our Nash equilibrium. Nash equilibrium is S1 2, S2 2, or we can write 3 comma 3. Okay, we can do it in this way, and there is another very easy and shortcut way that I'm going to discuss it with you. Instead of writing, although the procedure is same more or less, but if you could just underline the payoffs that both the players are choosing, that makes it relatively more easier to find that whether or which payoff is actually the Nash equilibrium, because here luckily we only have one Nash equilibrium, but there can be situations where there are more than one Nash equilibrium can exist, right? Okay, so erasing this thing, and let's play the game once more. So player 1 playing S1 dash. So player 2 have to choose between 10 and 12. So 12 being the higher, player 2 goes for the 12, that is S2 2 strategy. Similarly, if player 1 plays S1 2, player 2 again have to choose between 0 and 3. So player 2 goes for 3, which is higher than 0, and it is strategy S2 2. Now, so player 1 is done. Coming to player 2. Player 2 plays S2 1's strategy. So player 1 has to choose between this 10 and this 12. So comparing, 12 is higher. So player 1 goes for the S1 2 strategy. Similarly, if player 2 plays S2 2, then player 1 has to choose between this 0 and this 3. So here again 3 is higher. Therefore, player 1 goes for strategy S1 2. So here see, it is the only payoff where we have underlined both the elements, right? So from here we are very much sure now that this is nothing but this is the Nash equilibrium of the game. Okay, so this is not exactly what they have wanted us to find. What is the question? They want us to show that this unique pure strategy Nash equilibrium is not Pareto optimal. So, what do you mean by Pareto optimal? See, it is a situation where none of them can be made better off without making any one of the player worse off. Then only that situation is known as the Pareto optimal situation. So we can write over here that it is the situation where no one is made better off without making anyone worse off. Okay, so this is the basic definition of Pareto optimality. Okay, so here we have got Nash equilibrium to be our strategy 3,3, right? Now if we look at the game properly, there is a payoff which is higher than 3,3, that is 10,10. So at this level, both the players can be made better off because both of them, the payoff is increasing, right? So from here we can say that yes, this Nash equilibrium is not our Pareto optimal situation, okay? Because if any of the players goes off this Nash equilibrium strategy, that means if S1, or that means player 1 chooses this S12 or this S11, and if player 2 chooses similarly S2 dash, then we can say that yes, whatever the question they have asked us, that we have to show that this Nash equilibrium is not Pareto optimal. So we are successful in proving this thing, right? Therefore, Nash equilibrium, what we have obtained, is not the Pareto optimal condition. Okay, because under Pareto optimal condition, the condition would be 10,10, which is higher than the Nash equilibrium situation of 3,3. Alright, so we are done over here. Next part of question number 3, coming to that part. Okay, so in question 3, part C, here we have a question from the market, and we have a Kuno market with inverse demand function that they have provided us with A minus ABQ, and here A is positive, Q they have defined us as Q1 plus Q2. And they have provided us with the average cost of C. So from here we have to find the total cost, which is CQI, and I can take value 1, 2 because there are 2 firms in the market. Okay. So we have to find the pure strategy Nash equilibrium of this Kuno system. Okay. Alright. So this is the inverse demand function, and this is our cost function. Now, so there are 2 firms. That means we have to find the profit function for 2 different firms. Alright, so before that we have to find the total revenue for both the firms. So total revenue is our P into Q1, and here P is this whole thing into Q1, and here we have total revenue for the firm 2. So this is A minus of Q1, Q2 and Q2, right? Now we have to find the Profit of farm 1, or rather we can say profit function of farm 1. Let's denote it by pi 1. So what is it? It is total revenue of farm 1 minus the cost of farm 1. Here Qi can be replaced easily with Q1. Okay. So our total revenue is this one, A Q1, B Q1 square and C Q1, right? Okay. Now we have to do let's find the profit function for farm 2 as well. That is pi 2, and here we have total revenue of farm 2 and this thing minus the cost function. So here we have the total revenue of farm 2 over here, that is minus of B Q2 square, right? So we will be needing this one and this one. What are these? These are the profit functions of both the farms. Okay, now I'm just erasing this part. Okay, so first order conditions, del pi 1 by del q1, it is A minus of 2bq minus bq minus c equal to 0. Here we have to find q1 in terms of q2. So this is the thing that we get. This is known as the reaction function of farm 1. Okay. Similarly, the first order condition or differentiating the profit function of farm 2, which is equal to A minus of BQ1 minus 2BQ minus C, and this is equal to 0. So here again we have to find Q2, which is in terms of Q1. Alright. So A minus BQ1 minus divided by twice of B. And this is the reaction function of farm 2. Right? How the reaction functions look like? Let's draw the reaction functions. So here we are measuring the output of farm 2 and here output of farm 1. Okay, so reaction function of farm 1. If you find that it is difficult for you to derive the reaction functions from exactly from this equations, we can also solve it a bit and then we can finally come to our reaction functions. Okay, so these are the reaction functions of the two forms. Now we have to find the value of Q1 and Q2. As we can see that in Q1 we have the term Q2 and similarly for Q2 we have the term Q1. So we have to separate it and find it. Okay, so we have used equations till 2. Let this be equation 3 and this be equation 4. Now substituting 4 in 3, what do we get? Okay, so we have Q1 A minus C by 2 minus of half, and in place of Q2 I am just substituting this value. Okay? Okay, we are going to do this later. Alright, so here we have A minus C twice of 4B, that is, and minus of BQ1 by 4B, so we can cancel these B terms, and we finally have it as A minus C divided by 4B minus of Q1 by 4. So this is nothing but equal to Q1. Now bring this term to our left hand side, and finally we can get twice of Q1 divided by 4 is equal to A minus C by of 4B. So finally getting Q1, which is only in terms of the parameters of our equation, that is the demand function. So we finally get, I'm writing it at the top, okay. Okay. So what is the thing that we are getting? Q1 star, we can write it as A minus C divided by 3B. So this is the output of farm 1 that will be producing. Okay. As it is a Kurno market, so here the basic characteristics of the market says that both the farms are choosing their output level at the same time. So this is again a simultaneous mood game. Okay, hence we can say that this Q1 star, what we have obtained will be exactly equal to the Q2 star as well. Although I'm going to show it, but this is also a logic that we can apply to save some of our time. Okay, so we have done, or we have substituted equation 4 into 3 to obtain Q1, that is the output of farm 1. Now we have to do the opposite thing. Okay, so Q1, let's just write it over here. A minus C by of 3B. Okay, so now substituting equation 3 in 4. So we have A minus C by 2B minus of Q1, or we can say half of Q1. We can just substitute this Q1 from equation 3, which is A minus of B by C minus C divided by twice of B. Again we have to substitute or simplify a bit. Minus 2C, and over here A minus 2C by 4. I've already eliminated these B terms. Okay. Now coming to the next portion. Okay. So here we have A minus C by of 4B, and again bringing this term involving Q2 to our left hand side to obtain the final value of Q2, and that would be, so here again 3Q by 4, 3Q2 by 4 is equal to A minus C divided by 4B. So finally we are getting Q2, or again we can write it over here. So Q2 is A minus C divided by 3B. So see, the output of both the farms under Kurno framework are always the same thing. Output level are always same. Okay. Now, they have told us to find the unique pure strategy Nash equilibrium of this game. Now, we are coming to the portion of reaction functions. Okay. So this is reaction function of farm 1, this curve, and this one shows the reaction function of farm 2. So here the point where the two reaction functions are intersecting with each other is the point where the Coulomb equilibrium occurs, or we can also denote it as Q2C or Q1C. Okay. Now we have seen that in the beginning of this question we have already started with the answer with definition of Nash equilibrium. Here it comes here again that Nash equilibrium is a situation where both the players are choosing the same payoff and they are all better off, provided that none of the other player is choosing different payoffs. Here the payoffs is nothing but the output of the farm. Now, so farm 1 is choosing this Q1 star, the value is over here, and Q2 star for farm 2. In this case, we are already finding that both the farms are choosing the same level of output. Hence, we can say that this Coulomb output are nothing but the Nash equilibrium of the game, but here the game is again in a Coulomb framework. Okay, so these Q1 star and Q2 star are the Nash equilibrium of the game. Okay, so this is the thing that they have asked us to find out. So this is how you need to solve some of the questions. And if you have any kind of doubt from this video, please let us know at our official site of Sources Classes. Thank you for watching this.